Hello. Thank you. Hi. That was quite an introduction. And Alyosha's talk was so good that I'm embarrassed to present after him because my talk is not going to be as good. However, considering that this is the last talk of the day, one upside is that my talk also has no equations or math. It just has a lot of pretty pictures and some diagrams. All right, so I will be talking at a higher level about deep learning as a field and the models that the research that we are seeing in deep learning, where it's getting integrated into products. And I'll talk about how there are certain trends that are appearing in deep learning that are growing, and how we sort of have to change the way we do research and we integrate deep learning into products based on these trends, and how we're building tools to cope with this. So my talk will be in 3 stages. In the first stage, I will give a lot of examples of the latest research in deep learning, not necessarily from Facebook, but entirely from the entire industry. And in the second stage, I will talk about what I call is a dynamic trend in deep learning, and I will get to this. In some time. The last part, tiny part, is I will talk about the tools we use when building AI research, building neural networks, and how these tools are starting to be categorized into 2 kinds of types, and what we need to build to enable the future trends of AI research in terms of tooling. All right, so start off. Some examples of AI research and products. The first slide obviously is Facebook stuff. So one of the examples that we've effectively integrated into Facebook itself is when you access Facebook from a blind person's interface. That is, they browse Facebook, but they can't actually see. So when they tap text, the text is read out to them. If I tap on something there, it says Sunday night splurge, and the text is read out to the person. However, until recently, only the text was read out, but if you tapped on a picture, it would say a picture, but it wouldn't tell you what is in the picture, and that degrades the experience a lot. Like, you can't know if there's a picture of someone laughing in the park, or a video of a cat chasing a mouse. I mean, these are things we really enjoy when we're browsing any social network, and the fact that blind people can experience them is not nice. So we integrated a tool where now if you tap on the picture, it would actually tell you what is in the picture. It would try to describe to you what the picture contains. And similarly, there's research being developed on not only captioning pictures, but also captioning videos. And this is a very impactful and effective use of AI, and it's also cutting-edge research that was deployed to 1.9 billion people. Here's another example. Self-driving cars, they're everywhere. You talk about it, you listen about it. I was even sitting in one of them once. And building a self-driving car involves a lot of deep learning research, but also a lot of traditional computer vision and a lot of other things. So the deep learning part of the self-driving cars involves doing stuff like stereo correspondence automatically, or detecting lane markings in various lighting conditions, whether it's raining or anything, identifying where the stop signs are, where different speed signs are, and so on. So it's a fairly complicated problem, but there's a lot of progress being made, and one of the core components here is a lot of deep neural networks that power these cars. And another very, very effective example is machine translation. You want, right now in this audience, there are many people listening to me as I speak in English, and you get a live translation into Russian. But what if there is no translator there all the time for you that is a human? Just as an example, I came here to Moscow and I don't speak any Russian. I want to go talk to many people on the street and say hi and know what they do, but I can't. I have a language barrier, and it's a common problem. Someone today asked me how Russian businesses can interact with the rest of the world, how they can do business, and how Facebook can help there. And I said, we will try to solve machine translation so that every person in the world can communicate with every other person without having a language barrier. And the way machine translation has been making strides, improving accuracy in what translation happens, is driven by deep neural networks. And this is going to be a common occurrence, of course. I'm going to keep repeating deep neural networks and deep learning because they are everywhere. So in machine translation, you use two kinds of networks, recurrent neural networks and convolution neural networks. And they basically drive all of your machine translation, and everyone uses this: Google, Yandex, Facebook, and there's a lot of open source code there. Primarily, the way you train these things is that you collect a data set. You collect a data set of pairs of sentences, one sentence in English and its corresponding translation in Russian or French. And so you collect pairs of sentences, you collect millions of pairs of sentences, and then you train a neural network to understand how to map one sentence to another. Just like how Alyosha in his previous talk showed how you can map Monet paintings to regular paintings and vice versa. So one of the things that you're going to see in my previous two examples is self-driving cars have a lot of dynamic components. You don't collect a data set beforehand and just use that. The machine has to be making certain decisions at runtime that are new. But for image captioning, we also collect a data set beforehand, and what a data set in this case is an image and the corresponding captions that the image might be predicted to be. And then you train a neural network that will take an image and generate a caption. Here's another example. This is the Sharp Mask project. Traditionally in computer vision, this is called semantic segmentation. What the task here is that you take an image and then you have to segment out every object in the image separately. So here, for example, there are several zebras in the image on the left, and the system has to accurately segment out each zebra separately. And this is useful in many, many places. The fact that you will have the system, you would want this let's say a very simple use case is you want to build a personal robot, like a home robot. You would want semantic segmentation because you won't want the robot to know where different objects are, how, like which part of their image sensor is seeing which object, and so on. It's a fundamental and hard computer vision problem, and we're making lots of progress on this problem because of neural networks. And the way this works is that you collect a big data set of images and their corresponding segmentation that is made by humans, and then you would train a neural network to do the same task. This is an even more complicated system of captioning plus segmentation. What you have to do here is you have an image, and then for each region in the image, you have to describe what is happening in that region. And this is called dense captioning. And this is useful especially when you're trying to describe more complex situations where many things are happening in the image, or let's say you have a video sequence where different things are happening in different parts of the video. And again, similarly, you would take a data set of images and their dense captions, which is even more cumbersome to collect, and then you would train a neural network to give you captions for each segment of the image. And some of the applications of the systems I've described are obvious. There are many apps that have integrated this technology. There are apps that you can click food and then it will tell you how many calories are there in the food. There are apps that will try to look at your human pose and give you tips, and apps that you can click any object and then it will tell you where to buy it, how much it costs, and so on. And the applications here are obvious. It's technologically augmenting your capabilities, just like how it's taking your, say, smartphone to the next level of intelligence. Here's one example that touches upon robotics. So this was an animation, but I think I screwed something up, so you don't get to see the animation here. But basically, this is work from folks at OpenAI, where there's a robot that it learns to do a particular task by seeing someone else do the task. So if you have a task of, say, move the red block onto the white block, then it's a simple task. And you can teach it in many ways. You can build a data set where you show the robot how to move the red block onto the white block, where the white block is in various positions. Or you can teach the robot how to generally control blocks first and then give it a subtask and so on. But more importantly, the robot has to learn this in an interactive fashion. You can't build a data set beforehand and say, here are ways in which you can learn from this static data set. The robot has to learn interactively how to move itself, how to look at itself and see what it means by moving, and then it can learn tasks. The most impressive thing about this research is that they have a system where the robot can train itself to do new tasks just by seeing one example of a human doing the same task. So if I have a robot that is my personal home assistant, then I can teach it to do laundry just by showing it how I do laundry, and then like every day it will just collect my clothes and go do some laundry. Of course, this is in its much earlier stages of research than building a home automation robot. But more importantly, the point I was trying to point out is that you cannot collect a data set beforehand to train this robot. You have to teach it interactively. Another direction of research that people have been going into is to make machines try to understand relational concepts, like or visual questions and answers. So an example is you have a small picture there on the right bottom, and then there's a question that says, are there more cubes than yellow things? And so your system needs to understand what cube is, what yellow is, and what thing is. And you can have similar questions that are more complicated. There's like, is the yellow cube to the right of the purple cylinder? And then you have to understand what right is, what left is. And in this case, having a neural network understand relational structures, understand how to parse the question, and then put it into some kind of program that would get interpreted, all of these things, the neural network itself becomes fairly more complicated than what you have seen in some of the previous presentations. You have a neural network that is essentially a computer program by itself, in the sense that it will have to learn how to do control flows like if loops and while loops or for loops to basically parse your sentence in some dynamic manner and then put the right representation that goes into your neural network that actually processes your visual part of this problem. So over here, you have your data set is static. That is, you can collect a data set beforehand that has the questions and answers and the images, but your neural network itself is fairly, I would say, dynamic, in the sense that it's not just a simple data set that you can, a neural network that you can just put together as building blocks. Another set of line of research that is coming through is memory augmented neural networks. Memory augmented neural networks are neural networks that train themselves to understand and use some external memory. So you can have a neural network that trains itself to, as it gets information, put that information into some memory slots that it controls, and then later it would read that memory while doing some other task. This is similar to, let's say, how you could read some article and then later answer questions about that article by referring to some facts from that article from your memory. And there's a lot of research going on in this direction. I only pointed to some 2 sets of works. But in this case as well, the model that you build is fairly complicated, that you can't really see it as some model where you send the input and out comes an output. There's a lot of stuff going on in there that's not just, say, a simple matrix multiplication or some pointwise function. And I would call this also the dynamic nature of the neural network. Some work on adversarial networks has been getting very popular. This is a small example of adversarial networks. Alyosha had given a few more, where you generate images. In this case, we generate faces, and then you can also do linear algebra on, say, the face representations. And even though the adversarial network has never learned what a face is or what components the face has, it learns these consistent interpretations of how to transform face semantics one to the other. And Alyosha had talked about his 2 works that I wanted to highlight. There's been a lot of work on adversarial networks, and talking about examples and research of AI today without adversarial networks is not going to be sufficient. Because Alyosha covered this, I'm obviously not going to cover this. And here's the zebra example he showed. It doesn't have Putin on it, but it's there. Lastly, I want to talk about how there's an explosive amount of AI research going on solving video games. And why do AI researchers try to solve video games? The answer is actually quite simple. Video games serve as a proxy for complicated real-world issues. Like Super Mario in itself, for example, is not useful if an AI solves Super Mario. But Super Mario represents certain things that are hard for an AI to solve that humans can solve easily. Same with StarCraft or Dota. You have these games that humans are very good at understanding and becoming good. But if you ask an AI to solve it, it can't, because it doesn't know how to play games in which the human player can easily do, where the situation is you only have partial information. You don't have full information of what the other player is doing. You have a lot of actions you can take for every time step. At each time step, as a player, you can choose one of, say, like 10,000 or 100,000 actions. You can build a new unit, you can move a unit somewhere else, and so on. And just having a large action space, having these imperfect information games, these are all very hard problems that if we built a robot, it would have to solve these things in the real world anyways. So researchers use video games instead as a proxy, because you can simulate them, you can control them, you can change them in various ways so that you can make research progress. And of course, you can also do even more crazy things. There's an interface called Universe that was released by OpenAI, where you can have neural networks or like any agents just go and interact with the internet. You can have a neural network that can learn how to book a ticket for you by Googling for tickets and finding the best price, and then just having your credit card on file, and like learn all of this process. And there's a lot of research going on in doing these tasks, because there's a lot of interest from the product side as well, to build chatbots that will be your personal assistants to automate all these tasks that you do routinely. And what these video games or interacting with the internet are again dynamic worlds. Like, you don't know ahead of time. You don't just construct what the internet is ahead of time. You have to interact with it as you train with it. So, concluding my first part of the talk, I showed you a series of applications in AI, and I sort of pointed out to you that you get different flavors in AI. You have static data sets, dynamic data sets, you have static models, dynamic models. More objectively, like, to put it in a nicer way, what I mean by the static data sets is that you have a data set that you collect beforehand, you have some model, and you train it on some objective, and you train it. After it's converged, you take this neural network, you take the weights of the neural network or something, and then you put it in your application, and you essentially deploy it. And whenever new data comes in, it goes through this neural network, and you get some predictions. And you use those predictions in your product. And you don't have any learning during your prediction time itself. The dynamic kind of neural networks, just to repeat, self-driving cars are one of the examples. Visual question answering, memory augmented networks, interacting with, say, a dynamic environment like video games. These are all the dynamic kind of neural networks. And one of the trends we're seeing is that there's more and more of research and products that are being built in this direction. I'm not saying the static kind is going less, but I'm saying there's more and more of dynamic neural networks coming into play. And as I put it, you can, with dynamic neural networks, like I only talked about the dynamic worlds here, but you can also have neural networks that can change their own internal behavior based on what data you get. So for example, you can have a neural network that has this shape. Let's say each of those colored nodes are some layers in your neural network. And when sample 1 comes in, it has this particular shape. But then when sample 2 comes in, some part of the neural network decides that it wants to change its structure according to the nature of sample 2. And this data-dependent change in model structure is what I call dynamic neural networks themselves. You can also have memory-augmented neural networks that decide at runtime that they need more memory capacity, so they will just increase the number of layers they have at runtime based on some internal criteria. So because we're going in this direction of having to have dynamic neural networks, we also need to empower our researchers and our developers to be able to do these things without making it really complicated for them. And my last section of the talk, which I've been personally working on, is how do we build tools that can cope up with this changing trend in AI research. And the needs of the tool we need to build are that you need to be able to interoperate easily with the dynamic environment. You need to be able to have the dynamic neural networks themselves that can change their structure based on, say, the kind of data they see. In general, you want to have minimal abstractions. That's just a sign of a good library. And lastly, you want to have your neural networks be fast, because everyone is impatient. You want everything to be as fast as possible. On the note of fast, one small thing I wanted to say was that at Facebook, we recently released a paper that shows you how to train a state-of-the-art neural network on ImageNet in just 1 hour, compared to this is the same task that routinely used to take us 2 or 3 weeks. And as researchers, you want to prototype the ideas that you're working on as fast as possible. So it was not always obvious on how to scale this up. And finally, we, my colleagues at Facebook, they've written a paper talking about how to principally do this and make training really fast. The thing that I skipped in this slide is that it trains in 1 hour on 256 GPUs, which most people don't have access to. Anyways, coming back, we want your tools to be fast as well. Now, there's many frameworks in deep learning. If you're building a product or if you're doing research, you almost definitely use one of these tools. And I would say you can categorize these tools into two kinds based on the talk I've given so far. One is static graph frameworks, and the second is dynamic graph frameworks. And static graph frameworks, they usually expect you to collect a data set beforehand, or like if your neural network has any dynamic structure, they want you to unroll it beforehand. What that means is if you have some conditionals or some loop variables, you want to pre-specify how long you want to unroll your loop for, and so on. And they're slightly harder to build research that of the kind that I said is dynamic in nature. So what I've been working on is working on this tool called PyTorch, and it's a dynamic graph framework, and it's equally fast as the other frameworks, and it's one of the most flexible tools that we've tried to build for research. And what it is it's an ND array library. So if you ever use NumPy or if you use MATLAB, you can use it as a replacement for that has GPU capabilities. And it has an automatic differentiation engine that is very different from the other frameworks, and it can support crazy models and research easily. And as a small example, I'm not going to go through this, but this is side by side of a NumPy program and a PyTorch program, and they're basically very, very similar. For the programmers in the audience, what PyTorch does with its AutoGrad engine is that you start writing an imperative style of program. You just write your code as you go. And then in the background, what PyTorch is doing is it is building your neural network as you're writing the code in the interpreter. And when you are ready to train your neural network, in the final, after you've finished building your neural network, you just call backward on the last variable, and then gradient optimization happens automatically. And this is my last slide. It's just a sell for people to try the thing I've been working on. And I hope you found my talk useful, and I will take questions.
Можно микрофон?
Thank you, Soumith, for your talk and for the work you are doing with Torch and PyTorch. I'm actually one of the users of your package. Could you please maybe share with us the next plans for the features you are going to release in the next PyTorch stable release? Thank you.
Sure. In the next PyTorch version, we're going to be releasing distributed training. So you can train on as many machines as you have, as many GPUs as you have across machines. The second feature we're going to release is doing higher order derivatives. Right now in PyTorch, you can only do up to first order derivatives. In our next release, and that's going to be happening in a couple of weeks, you will be able to do arbitrary differentials. Basically, you can compute Hessian vector products and so on. Those are the two main features. In the longer term of, say, 3 to 6 months, we are working on aspects of speeding up your dynamic computation by introducing a JIT compiler. So you would write your code as is, but in the background, when it's possible, PyTorch will queue up your computation and accelerate it by fusing kernels and so on. So these are the three main features we're working on.
Next question.
The access to the Facebook images, is it possible to use freely, or do we need to make some legal agreements? For example, the whole set of photos, for example, what you have as a company.
To be completely honest, I don't know the answer. I haven't read the document that says what the image rights are. I just clicked I agree. So you should ask someone who's a lawyer.
Okay. Yes, there is a question in the back.
Thank you a lot. You were speaking mainly about narrow AI, but did the paradigm shift for general AI? What is your position about that? Maybe a forecast?
The question, if anyone heard, is I was mainly focusing on narrow AI, and there's the whole question about general AI. In general, what we mean by general AI is that a single AI agent that should be able to do multiple tasks at the same time, that's somewhat intelligent like humans, who can adapt to and do new tasks, rather than just if it learns to do image recognition, that's not the only task it should be able to do over its lifetimes. I only covered in my talk applications of AI that are present now that are narrow AI. Agents that only learn to do a particular task. There's a lot of research going on in the direction of general AI. The fundamental problem that people are trying to tackle is what we call catastrophic forgetting. What this is that your neural networks have this property that if they learn a particular task and then they learn a second task, they will forget how to do the first task. So this is a problem when you're trying to have one neural network try to do many different tasks. There is no clear answer or direction on like how we're going to solve catastrophic forgetting, but there's a lot of people trying a lot of creative ideas to try to get around this. Because it's super speculative research, I didn't cover it in my in my talk.
Okay, maybe there are some final question.
There.
Thank you. I would like to ask you a question about, is it PyTorch, is it a low-level framework, or it is high-level like Keras? What's the difference? Like, for example, as I understand, a low-level framework, for example, is TensorFlow, and Keras is high-level. What is PyTorch?
PyTorch is all level. You only have one level that is both low level and high level. We show that with our design that you don't need to have a low level framework and a high level framework. We just do one framework and do it really well, and you wouldn't need two separate levels.